Hey, how's it going? Hello, Amin. Hello, Antonio. Happy Monday, Kate. Good afternoon, Shrek. Ando says, release the donk. That's what we're going to do today. Hey, Belka. Happy Monday to you. Hello, Pika. Hello, Nookus. Hey, Michael Scott. Welcome. Loved the video. I'm so glad, Pika. Now it's like, it's that time of the semester. Everybody's feeling it. Hey, Quarone, happy Monday to you. The hat is back. Anyone else forget to put their controller in the Google Doc? Hey, you can throw it, if you still want to test your controller, you could still throw it on the dock. Feeling pumped after that video? Good for you, Link. The Windbreaker. Oh man. Oh my goodness. My wife Hannah was out shopping and oh wait, I had the wrong camera. And she saw this and she was like, I thought of you. Yeah, this is... Can we meet Hannah? Maybe. She's not home right now, but maybe one of these days. Yeah, this jacket. Oh my gosh. Oh my gosh. Yeah, so this is my new favorite thing. That's funny. Looking very 1992. Nuka says, waiting to see my controller not work. Hey, you know, I tested a couple this morning, and the ones I tested were working. And you know, okay, so if you're not aware yet, today we're gonna test out some of the controllers that you guys made. And there's no pressure. There's really no pressure. This is just for fun. You know, because usually when you make a controller, you get to try it on the hardware, and then you'll have to make adjustments because donk or donk not, there is no try. No, but my point is, usually you'd have the luxury of having this equipment in front of you, and so if your controller doesn't work, you could just iterate on it. But in this case, you just have the one design that you made in simulation, and we're really not sure if it's going to work. But the ones that I've tried so far have worked. Yeah, so this will be fun. This will be fun. Let me tell you what I want to do. Let's see here. The donkness awaits. So if you want to try out your controller today, there's a Google Sheet that I posted on UB Learns. That's a quick way to throw your parameters in. If you don't want to try, you don't have to. Really, there's no pressure, but that's what we're doing today. Let's see. So I already put in a bunch of your parameters, and so we can just one by one, and this is just in the order that they were received. So let me tell you the test that I want to do. We're gonna do a step reference. Let's see. I think I want to do this. So we'll try a step, and it's gonna like alternate directions. And we're also gonna do a ramp. And then another thing that I want to try is I have this potentiometer, And I still have to make this code for it. We'll put it together really quick. But I'm going to change the reference signal by changing this dial. And I want to see how the controller keeps up with that. So that's just kind of fun. So this will be like not a ramp, not a step. It'll just be like an arbitrary reference. Okay. 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 Let's get started then, huh? Let's get started. What are we waiting for? The first one that we're gonna try. This is the one that Amin submitted. If you're here, Amin, let's go back over here. Okay. Oh, so let's talk about the controller really quick. Okay, cool. So we're gonna try yours first, Amin. Remember, there's no pressure, there's no embarrassment. If it doesn't work, whatever. But is this what you guys got for your difference equation? I have the voltage at this time step is equal to the sum of the poles times the voltage at the previous time step minus the product of the poles times the voltage 2 time steps prior plus your gain multiplied with the error from the previous time step minus your 0 location times the error at the 2 time steps prior. So this is just using backwards shifting theorem. Didn't solve it generally, have to double check. Okay. But so this is the code that we're using. Which is really cool. Like looking at this, it's like, how would you think of making a controller like this? Well, you could explain it to somebody now. Okay, so we're gonna do a step reference first. So I gotta turn off the ramp. I gotta check up here. So the ramp, I mean the reference that we studied was 2 pi radians per second. Let's try that one first. And what I want you to look at is, as your controller comes up, think about like, does this behave like what you saw in the simulation? Oops. Okay, let's look at... Okay. So what we're looking at here, just to refresh your memory, the blue line is the reference signal. The green line is the angular velocity of the motor, and the red line is the voltage. And remember, we only have a 6 volt source. So look at this, look at this. Yeah, this looks great. So we have like 0 steady state error. Now, the time here, like I'm alternating every 4 seconds. So it looks like it settles in like 1 second or something. It has a little bit of an overshoot. Never thought my school projects would actually work in the real world. No, this is working very nice. Okay, let's try a ramp. Let's try a ramp. Let's try a ramp. Let's see how it looks. Let's see. Borat says, very nice. This is pretty nice. The steady state error. Wow, wow, wee, wah. I mean, it looks like, I mean, with the noise, it's difficult to tell, but it's like right, it's very close to the reference. Interesting how the overshoot is not the same every time. That's right. That's exactly right. Okay. Amin, this looks great. Let's move on to another controller. All of these are going to be a little different. Okay. I'll try to get efficient here. Okay, so I got to comment out a mean, and then I have Mike. Is Mike here? Let's try it. Let's upload it. So we're gonna start with the ramp. This one's a little different. The 0 is in a different location. Oh, great question. Why does that happen when it crosses 0? Oh. Okay, the reason it has an issue when it crosses 0 is the motor has what it's called a dead zone. When there's low voltage, the motor can't actually spin. Like right here, there's not enough voltage to make it spin, so it just flattens out until you create enough voltage and then it can spin again. So it's kind of like friction in there. So this controller is also doing great. It has a little more steady state error on the ramp. Let's try a step. Let's try a step. We're gonna try this. Nice. So no steady state error. It looks like it's settling in around like 3 seconds on this hardware. And remember, your simulation might behave a little different than this controller does. But I would say this controller is also doing a nice job. This little square thing is from the dead zone once again. It just doesn't have enough voltage there to make the motor spin. All right, let's try another one. Let's see. Nicholas. Let's try yours. Ooh, this one has a little more overshoot. It's pretty fast. Let's see what it does. It's about to switch. So this one has a little bit of overshoot. No, Nookus, this is nice. This is fast. I don't know, this settles in like probably a little less than a second. Let's try a ramp. Okay, we're gonna do this. We're gonna do this. Bad controller? No, I think this is fine. This is meeting all the performance requirements. The steady state error on the ramp is very small. Okay, we have the dead zone, so it's gonna boot up again. Look at that. Okay, we gotta try the next one. This one, Fly Little T. I don't know if you're here, but we're gonna start with the ramp for you. After this is the guy who stinks. Oh my gosh. Oh dear, what are we gonna do about that? Ooh, interesting. You don't remember? Oh, there was... Okay, I'll tell you what happened. I mean, it's just the name of the person that submitted this that... It's like that guy who stinks at picking poles or something. That's the name. Okay, wow, this has very little steady state error on the ramp. So the KV is going to be very large. Okay, let's try this. We're going to try the step now. There's a bunch of oh, Liam is the imposter? Liam, what did you do? Okay, so this one has a little bit of overshoot, some oscillations, some extra oscillations here. So for this one, you'd be able to go back and just iterate on your controller a little bit. In case it didn't work, Liam just wanted to have somebody to blame. Yeah, let's see this. This is the guy who stinks at choosing polls. Okay. But we know it's you, Liam. Okay, let's go to the plotter. Actually, this looks very nice. This is pretty quick. Very little overshoot. Zero steady state error. Let's look at the ramp. Is it gonna do well with the ramp? Tell me the truth. Are you an imposter? Seems to be doing very nice. Well done, guys. And you didn't think it would work. You didn't think it would work, did you? Okay, next is OJ Boat, and then Belcut is after that. So OJ Boat, we're starting with your ramp. You had to hedge your bets, I get it. Very nice. Very little steady state error when following a ramp. Let's look at your step response. Okay, let's see how this does. Okay. A little bit of overshoot. No problem with that. Let's see what it does. Very nice. This class is producing scientists. That's right. You know, there's no big mystery to control system design. Belkit, it's you. Okay. Nervous laughter. Now don't worry if it doesn't work. Okay, there's... Oh, this one. Look at this. It looks like it's very quick, but there's no overshoot at all. Oh my goodness. This settles, it seems like, in a little less than a second. No overshoot. Or just very, very little. Wait, what did you, what was your overshoot designed to be? I'm kind of curious. Yeah, this one's yours. This one's yours, Belkit. Okay, let's do a ramp. It's quick and has like very little overshoot. I like that. 0.05 overshoot. Just got in from getting my tire replaced. Did we do yours? Mike, I think we did do yours. I can go back. Just submitted mine if there's time to grab it. Yeah? Oh, did I change something? What did I do with my ramp? I don't think it's you. I think I commented out the wrong thing. Let's see. Oh, I left this thing on. I'm doing like a combination of a square wave and a ramp. Okay, that's me. Belkit, what did you do? That's kind of interesting what it was before. Yes, very nice. Okay, we're gonna do Mike really quick. We're gonna go back. Mike, you better get ready. Because this is you. We're gonna do your ramp first. Okay, so the steady state error on the ramp, you can see it's a little bit more tolerable. Okay, let's check out the step. Let's look at the step reference. Come on now. Okay, so it has no steady state error. It goes to the speed that we set. And it looks like it takes, on the hardware, it takes about 2 or 3 seconds to settle. Nicely done. Okay, so we're gonna do, wait, I think it was Mark next? Will we cover how you determine the given plant transfer function? Yes, Jim Alina, we actually did it in lecture one day. We determined it together. I forget what day it was, but we did like a system identification test. There's a couple ways. Okay, so this one has, what does this overshoot? Maybe like 20% or something? Let's look at a ramp. Oh, yeah. Very little steady state error for the ramp. Oh, I did the same thing again. This still gets the job done. I think a while back. Yeah, it was a while back. It was one of the it was probably within the first month of classes. Okay, guys, what I want to do, I'm going to unplug this really quick, and what I want to do, I want to make a code really quick so that we can have this potentiometer change the reference for us, and then we'll continue testing everybody, okay? But I have to make some code. Okay, so int, this is the pin that I'm plugging the potentiometer into. So we'll put that in there, and then we'll have the analog to digital value from the sensor, and then I have to convert that into a speed. So this number is going to be between 0 and 1023 as I twist around the potentiometer. So we have to map this. Okay, let's throw this in here. Analog read from the potentiometer pin. So we're gonna read from the sensor. Wait, let me check up here really quick. Did I name these variables right? Potentiometer pin, pi ADC. So pi ADC equals that. Okay, and then We have to say the reference at time k is that ADC. Let's divide it by 1023. So now it'll be a number between 0 and 1. And then I'm going to multiply it by 3 times pi. Wait. 0, 1 times 3 times 2. So what this will do, if I turn the potentiometer full to 1023, it'll get up to a speed of 3 revolutions per second. I think that's probably at the max end. Okay, so we have to make another section for this. Reading reference from sensor. Oh my gosh, should we try it? I think this is all I have to do. Oh my gosh. Okay, let's turn off the square. Is there a reason you put 1023.0? Yes, because for this number to evaluate to a double, you have to put a 0.0 in Arduino. Because if you divide, so it's weird. If you divide 1 by 2 in Arduino, it evaluates to 0. But if you divide 1.0 by 2.0, it evaluates to 0.5. So I have to do something like that. And I think this will work. Okay, so we're going to turn off the square. We're going to turn off the ramp. And all we're going to use is this. Oh my gosh. What do you think is going to happen here? Good grief. Is this working? Oh. I'm twisting the potentiometer. See, this is the beauty of your controllers that you made. It can really follow, I forget whose I'm doing right now. But you know, we designed like doing a ramp and a step. Oh ho 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 ho. Okay, that's cool. That's cool. Let's move on to he added some, yeah, I just added a potentiometer. If you're taking 334, this is something you can do to your codes now. Okay, now we're doing H-Swan. Can you use this potentiometer to determine the limit of the dead zone? Yes. Oh! Now what's happening here is I think we can fix this. So this is an unstable controller, okay? Number one, this is unstable. But I think what happened is I think you intended for these to be positive. That's what I'm guessing. I think. How is it working? Oh, this is when the controller was going unstable before. And this is 4.0 times 10 to the 9th. That's the voltage that it was trying to call. So you have to be careful. When you make an unstable controller, it's going to go right to the limit of your control voltage. And, okay, let's adjust this. So once again, I'm just playing with the potentiometer right now. And it's following very nicely. Now, the higher you make KV, the less lag there is between the signals. Okay, let's do a step, let's do a ramp. Okay, now we're doing So I have to comment this. I got thrown off by the song that sounds... Yeah, there's music in the background that might, Okay, very nice. We got a little bit of overshoot, maybe 20%. Will you provide this Arduino code? Sure, I'd be happy to. I'd be happy to give you this code. Okay, let's move on. Next is Kate. We're gonna try out your controller, Kate. Get ready. Ooh. I think this one is gonna have very little overshoot, but it's still very fast. Let's see. Yeah. Do you remember what you chose your overshoot to be? That looks really nice. And it settles in around like 1 second. Oh, I could have a Boolean variable instead of commenting out sections manually. Yes. You're absolutely right. And it would be much more efficient than what I'm currently doing. Okay, we're doing a ramp. Or a switch case, yeah. Oh, Mitchie says, you seem smart, but I was looking for a hot tub. I'm sorry to disappoint. This is very nice. Very little error for a ramp. Very nice controller, Kate. Okay, let's do Isaiah. Isaiah is next. If this robot was carrying an external load, would the response be different? Yes. Yes, it would. Now, Pika, that's right, you're next. This is a very nice controller, by the way, Isaiah. Okay, let's, to answer your question about the load, we got this model for the motor with the wheel attached. Ooh, I have an idea. If I rub my finger on this, I'm effectively changing the load. But notice, the controller still fights. Look at the voltage. The voltage keeps increasing to try to make it work. Isn't that amazing? That's because we have an integrator. Well, if you have a pole at 1, it makes your controller adapt like this. So this is what it looks like without. Oh, this is very nice. No overshoot or anything. But if I try to stop the motor with my hand, look, it still has 0 steady state error. Or it tries to. It just gives more voltage. So did we make a PI controller effectively? It's definitely PI. I'm not sure if it has a derivative control to it also. To tell you the truth, I'm not totally sure. If you provide the code and we use a different motor, we have to change the transfer function and follow the steps of the project. That's right. But I believe if you can do it for this motor, you could probably do it for most DC motors. Okay, let's move on. We got so many more to try. Oh, Pika, it's your turn. You don't have high hopes? Look at this. Looks like it's doing great. It settles in about 1 second or something. Let's do a ramp. And I'll comment this. If it's a little slow, that's no problem, because you can, in real life, always come back, make some adjustments, be like, ooh, I want this a little faster. Very nice. There's our dead zone again. We needed enough voltage to overcome that, and then it's back to normal. So this is okay. You can do another iteration. Tighten it up. Okay. Joe. Are you here, Joe? And then it's going to be Gabe next. Oh, look at that. Very little steady state error on the ramp. So this has a very high kV value. Let's do a... Oh, we're not going to do... Oh, we're going to do the potentiometer now. We're going to hit it with like an arbitrary input signal. Let's see how your controller responds. Oh, are we going to do a burnout? We're going to do the max? Now, effectively, you guys have designed a servo motor. This is what a servo motor is. It's a DC motor connected to a feedback loop. And you could modify this code to change the position of the motor instead of controlling the velocity. Okay, next. Gabe. Oh, this one's very nice. I think it has no overshoot and has a settling time of like 1 second. Oh, I can do steps myself. Let's do a ramp. This is the custom ramp made by the fine motor control of my index finger and thumb. This is like an etch and sketch, actually. Very nice. Ashish. And then JP is next. I see Antonio. Donk Life is in there too. Oh my goodness. Okay, this one has a little more overshoot. Let's do a step. Yo, the sound of the motor was working with the music for a second. That's difficult. Do you think we have time to do all of them today? I think I'll just have to pick up the pace a little bit. And I think doing this potentiometer, I'll probably just keep doing this because I can do a step like this. And I can see this has like 20% overshoot. And then I can do a ramp like this. And this has very little steady state error. This is very nice. Well done. Why does the overshoot seem larger on higher frequency steps? Oh, this has interesting. Okay. JP. Let's go. Okay, it looks like we have maybe 15% overshoot. Maybe even less. And let's see how it does on a ramp signal. Follows very closely. Antonio, what do you got for us? Maybe I'll go back to a step again. Okay. What is this? This might be like 30% overshoot. A little bit oscillatory. Let's look at the ramp. Oh, it has very little steady state error. That has very nice ramp tracking on it. Very nice. Uh-oh. It's time for the donk life. Yeah, very nicely done, Antonio. Oh, this is nice. Not very much steady state error tracking a ramp. Let's check out the step. What's that step response? Oh, that's very smooth. No overshoot. 0 steady state error. It settles in about 1 second. What did you pick for the overshoot? Dan. Dan, it's you. Are you here? If we don't cover all these today, are we going to continue on Wednesday or will we go over today? I think what I'm going to do is I'm just going to stay on. We'll keep this party rolling and we'll just knock these out. So if you're waiting for yours to come up, my plan is to keep rolling. We're going to get the job done. Very nice, Dan. I'm here and feeling a little self-conscious for all these decimal places. Very nice. What program is this on? This is on the Arduino IDE. You guys can now say you've designed a digital control system for a DC geared brushed motor. This is real life. Andrew, let's see, how many do we have left? I got Andrew, Edward, Joshua, Ando, Primordial John, Chong, Jamalio, Galapagos, Andrew, BJ, Not, UB. Wait, who's this? Who is this? Andrew, Benny, Gage. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Let's go. Whoa. This one's unstable. Let's take a peek. Let's take a peek. Yeah, I think this one will be. I think this one will be. I think this one will be unstable. Because I think. I'd have to double check what the closed loop poles are on this one. But I'm guessing it doesn't. If your open loop zeros and poles are outside of the unit circle, it doesn't necessarily mean that you're unstable. But I think in this case it is. Is this related to an undergraduate course? It is a mixed undergraduate and graduate course. And it's yeah, I forget what I was saying. Okay, Edward. Your controller's up. Ooh, nice. It'll zoom back in a second. Here we go. We just need to get this off the screen and then you'll get to see. Okay, very nice. Very nice. Here we go, here we go, here we go, here we go. Square wave. Let's hit it with the square wave. Ooh, nice. No overshoot. Settles in about 1 second. There we go. Well done, you guys. Okay. Joshua. And then Ando Bear. Let's see it. There we go, Joshua. Very fast. Small amount of overshoot. Maybe that's just like 4 or 5% overshoot. Check out a ramp. Very little error. Gotta go take a test. All right, see you later, Tim. If you want to try out your controller, we can do it in office hours too. You can shoot me an email. Okay. Ando Bear. Followed by Primordial. Ooh, this one. Let's see. Let's see. Okay. So this one is stable. Very little error when tracking a ramp. But the transient performance, I would want to dial this in a little bit more. Let's look at the step. Here we go. Okay, so the damping ratio is just very low for this. It still has 0 steady state error. So this just needs to be dialed in a little more. Not bad, not bad. Okay, primordial. That one is the most aesthetically pleasing, that's true. Okay, here we go. This one settles in like 2 seconds. Donko, I've got a feeling we're not in Kansas anymore. Okay, let's check out your ramp. This looks good. Let's check it out. Oops. There we go. Not bad. All right, who's next? Who's next? John. John Anderson. Followed by Chinghan. Let's see the ramp. Oh, that is nice. That has very little error. So this will have a little bit of overshoot, which is totally okay. Let's see. Let's check it out. Let's look at the step. Let's see some overshoot. Oh my gosh, that guy who stinks and that guy who does not stink. Very nice controller. Very well done. Okay. Chinghan. Are you ready? Let's look at your controller. Wrong one. This is very nice. No, it definitely worked. Well done. It's always fun to bring the equations into a real life application and be like, hey, that's kind of what I thought would happen, but I don't know. It always seems like a miracle that it actually does work, but it does. Very nice controller, Chinghan. Jamalio. Let's put it on here. I want to see this work. Very nice. This one seems very responsive, low KV, I mean a high value of KV. Let's do a square wave on it. Yeah, this one's great. We'll upload this one. Let's see the ramp. Or wait, the step, rather. Ooh! Maybe like just a couple percent overshoot. Pika says, do we still have the literature review due Friday for the grads? Yes. At least tentatively. Oh, I like this controller a lot. I'm curious what Project 2 will be about. Project 2 is going to be related to a self-balancing robot. I don't know if we're going to be able to test it on hardware like we're doing for this, just because Um, that one's a little trickier. Galapagos. Let's do this. Ooh, this one's a little different. I'm interested. I want to make my own self-balancing robot so bad. Yes. Can't we use Wall-E? You know, I could... It's just the modeling is... Well, we'll talk about it. We'll talk about it. But the modeling is a little trickier. You actually got one, but it doesn't work? A Wall-E? Alright, let's look at the ramp on this one. Your Wall-E doesn't work? Alright, where are we? Oh, this has very little KV. I mean, very little ramp error. It seems like there's a trade-off. Like, your transient performance, like you'll get a lot of overshoot, but your ramp tracking will be very nice at steady state. Andrew followed by BJ Reiner. Andrew, you know what I'm going to do for yours? We're going to track the potentiometer. We're going to put it to the test. We'll see what it does. Let's get to work. Okay. Very nice. Very nicely done. You've developed a speed controller here. Works very nice. Okay. We're gonna go to BJ Reiner. You're also getting the potentiometer, so watch out. Look at that tracking. Yeah, nicely done. Boom. This has a little bit of overshoot. Maybe 20%. Settles very quick. Wow. We have a bunch of controls engineers here. Wait, this says not UB math professor. What does that mean? Who is this? What's going on? Did UB math professor make one? Dr. Estes, could you also add my controller to the list after you finish the last one? Sure. I'd be happy to. This is a lot of fun. Okay, this one has a little bit of overshoot. But settles very quickly. Okay. We have another Andrew here. Followed by Benny. Followed by Gauge Link. And then I'll check out any extras that you guys want to do. Ooh, this one's zippy. A little bit of overshoot. Nice tracking. I feel like this one has very nice ramp tracking. It can really keep up. All right, Benny. You here, Benny? Let's test it out. How many Andrews are in this class? I don't know. It's quite a few. Oh yeah, this is working nice. Let's look at the step. Just a little overshoot. Maybe 10%. Let's look at the ramp. Look at that. Pretty good. All right, gauge. Is it possible to do even better? Something that looks almost like the reference? Yes, but we would need, I think, a different parameterization of the controller. So this controller has 1, 0, and 2 poles. Wait, why is it doing that? Oh no, this is working great. I think we would need to add, so if you have 2 poles at z equals 1 for a digital controller, you can have perfect ramp tracking. But then we would need more zeros in our controller to make sure that it turned out to be stable in the end. Very nice, Gage. This is great. Okay, what I'm gonna do, I'm gonna turn this off really quick. I'm gonna put in Chinma. Let's try this. But then I'm gonna go to the Google Sheet because I know a couple of you uploaded, and I'll go there and grab those. Let's do this really quick, just because I had it right here. Shima. Let's try it out. This is so fun, guys. I'm really, this is really fun to check out. I think this is working very well. We'll just have the screen reset in a second. Hey, see you, Amin. Great work. Hey, you're welcome, Benny. This is a lot of fun for me. I hope you guys enjoy it. So what I'm gonna do, I'm gonna go to this view just for a second because I'm going over to the Google Sheet and I'm picking up a couple more. Gauge. Oh, Therese. Okay, we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 more. We're gonna do them though. And the Cowardly Bean just submitted. Brandon says, will the solution for this project be posted? Yes. Yes, I will. Okay, so where is this? Where's this thing? Okay. Good. I made this code to quickly import these. And so this should be quick to bring into my code. Let's see. Are you gonna work? Yes. Guys, we're back in action. Just gotta go back to this view. Oh, yeah. So we have these ones left. We have T. Jackson, Mr. Brightside, Tim Darling, Quaron, Krishna, Mini Clops, James, that guy who the real one, In, Antonio, Sean, Cowardly Bean, Dark Shadow. This assignment looks fun. Where can I get it? If you shoot me an email, I'll send it to you. You can take a peek. It's fun. Okay, all right, are you ready? T. Jackson? Let's upload this. No, I was about to submit right now. Okay. You're ready. I know you're ready. Oh, this one's good. I want to do the ramp test on this one. Screen's gonna reset. There you go, T. Jackson. You've made a motor speed controller successfully. Let's do a ramp. Let's mix it up a little bit. Hey, see you, Kate. Thank you. We're gonna do this. Chinghan, I just heard my name. Then my computer went offline. Okay, we'll go back and do yours. We'll go back and do it. This has very nice ramp tracking. Okay, let's do Chinghan real quick. Wait, how far back was that? You're right here. Let's upload this. We're gonna do the ramp test on you. It's working very nice. Very little steady state error when tracking a ramp. And what about this step? Let's do this one. Oh, no reason to be sorry. You're good. Look at that. This is very nice. Maybe 10% overshoot. Very fast, very responsive. Okay, who did we have next? Mr. Brightness, I believe. Let's see what we have here. Oh, look at this. Fast, but very little overshoot. So the transient performance on this controller is very nice. What I'm wondering, does that mean that it's going to have more error for a ramp? I'm not sure. Wow, no, I like this controller a lot. I like this controller a lot. Okay, Timmy Darlington. Are you here, Tim? Are you ready? Very nice ramp tracking. All right, we're gonna go back to the potentiometer. Then I believe Quaron is next. Okay, very nice. Quaron, are you ready? Let's try it out. Let's give it a go. Okay, I think this one, it has a settling time. I think it's going to go to 0 steady state error, but the settling time is a little bit long. So what I think is happening, one of your closed loop poles is probably close to 1. So it's working, but one of your closed loop poles is just the magnitude is too large. It's too far from the origin. So then it's going to be a little slow. So I would just say check all of your closed loop poles. It's getting there. It's stable. It has 0 steady state error. It's just that it has a long settling time. All right, this is Krishna's controller. Krishna. Oh, nice. Very responsive. Very little overshoot. It tracks a moving signal very well. Nice. Next, mini clops. Oh, this one's... I don't know what to do with this one. Because it's an imaginary. I think I have to ignore the imaginary part. I do not know what's going to happen with this one. I don't know. Seems to be working. Just out of curiosity, for my code, I found the 2 exact closed loop poles matched for Z-Star. The 3rd closed loop pole was irrational. Then changed it. Yes. Ando Bear, you gotta keep... Hey, see you later, Brandon. Yeah, I heard about DMX. Alright, rip, man. Rest in peace. Ando, no, you want your 3rd pole to be closer to the origin than your other 2 poles. So if you have a pole that's close to 1, you're in trouble. All right, James. Then we'll do a couple more. Oh, nice. Got a little bit of overshoot. It's not terrible. It tracks a moving target very well. Nice ramp tracking. Can I submit a faster controller? Sure. We can push the limits of this thing. Oh my gosh. The real That Guy Who Stinks. Are you still here? Let's try it out. Please work. Oh, it tracks a moving... Oh, this is interesting. So, your KV is like really, really great. Like, look at how that... The KV is really solid. Like, it's right on top. We see that the only drawback is the transient performance. So if I really give it a step, it's gonna... But you know, that's something that depends on the application, because if you have something that's slowly changing like this, your controller is gonna be like right on top of it. Oh, it settled fine for your step in MATLAB? Well, yeah, you gotta remember too that the model that we have for this, not perfect. So it's normal to have to iterate on it a little bit. No, nicely done. This next controller is from In. Whoever you might be. No, the KV on that one was out of control. Okay, this one, a little bit of overshoot. Very nice ramp tracking. Pokemon Champion In. Very nice. No, this is a great controller. Alright, let's look at the next one. We have Antonio. More decimals included. Oh, good grief. Holy decimals. Okay, this one's got a little overshoot. The ramp tracking, real nice. We got some oscillations here. So the transient response got a little bit of extra overshoot. All right, Sean, prepare yourself. Your controller is about to be tested. Okay, this one, very underdamped. Hey there, Black Matt. We got the LED. Poles found. I made a mistake of minimizing the last pole, maybe. Wait, so that's 0.625. Wait, so that guy who stinks, is it is that third pole closer to the origin than the other two? I'm wondering if it's farther away from your target poles. This one has very nice ramp tracking, by the way. Okay, Cowardly Bean. I hope you're ready. Okay, so this one, the settling time is a little bit slower. It looks like it's settling in about 2, maybe 3 seconds. You have to check your third closed loop pole for that. So it has 0 steady state error. You just see that it's a little bit sluggish. Ashish, hey Dr. E, can you do mine again if you have time and can give a bit more feedback on what I can do to improve it? Sure. Okay, so what I'm gonna do, so is it always underdamped with better ramp tracking? That's a great question, and I don't think it's always that way, but I think for this particular controller, when it's a little more underdamped, it had much better ramp tracking. I think an underdamped controller typically has a faster rise time And that can be better for tracking a moving reference. All right, what I'm going to do is I'm going to check back on the Google Sheet and see. Okay, so I see there was 3 more submitted. So we'll do these, and then a sheesh, I can go back to yours. So I just have to update this, do this. Oh, whoops. And then copy this. And then paste it. Man, we did a lot of controllers today. This has been a lot of fun. My third closed loop poll is only 0.0004. So that means it would have little influence. Interesting. You know what might have happened though? This makes me wonder. So because there's a little bit of modeling error, even though you think from theory that the poll is at 0.0004, it might be on the negative real axis. I'm a little hesitant to place polls at the origin just because of potential modeling errors. Okay, so I have na. Are you here? Are you ready? Oh, this poll is like, this 0 is very close to the origin. This is interesting. Let's try it. I like that all these controllers are quite a bit different. And yet... Oh, this one's very, very responsive. I don't think I picked the best poll. Definitely gonna think about why that didn't work as planned for the rest of the week. Hey, you can definitely, if you come up with a different one you want to try, we can try it out. No. I think this is a good one. It seems like it's meeting the performance constraints. It might be a little too underdamped, like the overshoot. It's looking like it's 20 or 30%. Mini clops. I put the wrong value for Z1. Which one do you want? We can update it. Do you know what you want it to be? I'll do mics, and then I'll come back to you. And you can send me an update. Should I submit to the form again? Yeah, put it on the form again. Well, you could just throw it in the chat, mini clops. Oh, you already put it for this one. So I can try it? Let's try it. Ooh. Step response looks nice. Let's do like a ramp. Seems to follow very close. Nicely done. All right, Mike, we're trying a faster one, eh? Let's try it out. Faster controller, here we come. How fast are we talking? So it's working a little underdamped on the hardware, but the rise time is like really quick. Let's try a ramp on this. Oh, I want to do this. And I want to turn this off. Let's go. Let's do it. I bet the ramp is going to be very nice. At steady state, yeah. Yeah, Endo, I'll try that out for you. Yeah, this is very nice ramp tracking, Mike. Okay, Z1. Let's try this. Double. Okay, double P2. Double K. All right, let's do it. Okay, still oscillatory, but it has nice KV at steady state. So if we do the step, I want to look at the step. I bet it's going to look really underdamped. Yeah, I just think that the damping ratio is a little bit too low. Do you know where all three of your closed loop poles are? Whew. Yeah. Yeah, do you know where all three of them are? Because I think that... I'm guessing one of your poles... Or it might be the Z star you picked. This was a fun day. I really enjoyed this. I hope you guys enjoyed this. If you want to try out more controllers, I do have office hours today. Oh, Ashish, right? You wanted me to look at yours again. Let me I'm gonna pull yours up really quick. We'll take a peek. Minus 0.97. Oh, Ando, that's your problem. You have your third closed loop pole on the negative real axis. You want to make sure that that you never have a closed loop pole on the negative real axis. It's going to make a very choppy response. All right, Ashish, we're uploading yours. Also, you said my poles are probably a little funky. Should I try to work on that, or is it okay? I think Quaron, your controller does not meet the performance constraints. So it's if I remember, it was too slow. And I can't remember if it was really oscillatory. Okay, Ashish, this is the step response. So if I'm looking at this, I would say the overshoot is a little too much. It looks like it's around 20-25% or something. So what you need to do is probably, number one, check that your original Z star like target closed loop poles, that those have the right overshoot. So that's the first thing. And then the second thing is check where your third closed loop pole is, and just make sure that it is faster than your target poles, but make sure it's not on the negative real axis. Ando says, I'll try to fix it. What time are office hours? Office hours are from 4 to 5 p.m. I'll be on Discord. No, but this looks good. This is a good controller. So we're gonna wrap it up here for now. Hey, thank you guys. Thanks, Mike. All right, Ashish, that sounds great. Good work, my friend. It looks great. I'm gonna eat some lunch. Hey, later, that guy who stinks. See you all later. Thanks. This was a lot of fun.